Hi sir, this is Manideepa from CSC B section. Today I am going to talk about fragility of quantum systems. These quantum systems are heart of the modern technologies like quantum computers, sensors and communication devices. So however these systems are extremely delicate. Even a tiny disturbances can destroy their quantum behavior. So this fragility poses significant challenges for their practical application and stability. This fragility is one of the main challenges in making quantum technologies more practical and reliable. So, in classical systems, small disturbances do not usually matter much. But in quantum systems, practicals exist in states called superpositions. Superposition means where it can be exist in multiple states at once. So when these systems interact with the environment through heat, light, vibrations or electromagnetic waves, the delicate superpositions collapse. This loss of quantum information called decoherence, and it limits how long we can use a quantum state effectively. So fragility mainly comes from the environment noise, material imperfections and temperature fluctuations. So decoherence is just a loss in a noisy room. It is quite opposite of coherence. And quantum information slowly leaks into the surroundings and the system behaves more like in a classical one. And it limits the coherence time, reducing the usefulness of quantum states. So the longer the coherence, the stronger and more stable the quantum state system becomes. And this overcome decoherence is a central goal in quantum error correction. So external noise source includes electromagnetic radiation, temperature fluctuations, and vibrations. These disturbances includes errors and decoherence in quantum states. The physical materials used to build qubits, such as superconductors or ions, must be extremely pure and defect-free. Even small impurities can create stability or in, sorry, even small impurities can create instability. Many quantum systems must operate ultra low temperatures close to absolute zero to reduce the thermal noise. Maintaining such scenographic environments is expensive and technically complex, which adds to the challenges. So, the quantum error correction code helps protects quantum information from environmental disturbances. It implements these codes is complex due to the fragility of quantum systems. To overcoming the fragility, researchers use quantum error correction codes, mathematical techniques that detect and fix errors in quantum data. However, implementing them is hard because every operation itself causes more errors. Another approach is precise quantum control, using laser or magnetic fields to manipulate qubits with high accuracy. And also machine learning is also being explored to automatically adjust and stabilize systems in real-time systems. So materials that imperfections can introduce decoherence and reduce qubit coherence times. So these fabrication techniques need to minimize defects and impurities. So when we scale up from a new qubits to hundreds or thousands, new problems are arised. So more qubits are more interactions, which increase fragility. Scientists are now developing better materials, improving fabrication techniques and error tolerance to make these architectures to make large scale quantum computers possible. The goal is to create systems that are robust, stable and practical for real world use. So the qubit coherence and fragility are the coherence times determines how long a qubit can maintain its quantum states. These improves coherence, enhance the stability of quantum systems. Qubits are susceptible to various forms of noise that limit their coherence. Many quantum systems require ultra-low temperatures to reduce thermal noise, and the maintaining these conditions is critical for minimizing fragility. So, to controlling the quantum and precision control of quantum operation is necessary to prevent errors. Small inaccuracies can lead to significant decoherence and system fragility, and the advanced control techniques are developed in enhancing robustness. And the stability challenges are the stability quantum systems and are the scaling quantum systems, increasing complexity and fragility. Interqubit interactions can introduce additional sources of decoherence, and overcoming scalability issues is essential for practical quantum computing. So, in summary, the fragility of quantum systems is one of the biggest barriers to the advancement of quantum technology, but it also driven innovations. Pushing scientists is to create stronger materials, smarter to over control, and new error correction methods. Overcoming fragility will ultimately unlock the power of quantum computing and communication. Thank you for giving this opportunity.